Hello, this is Dr. Johnson. I'm one of the AP Stat teachers at Capel High School. Welcome to this lesson on describing locations of an observation within a distribution. One way to describe a location is to use the percentile. The pth percentile is defined as the value such that p% of the data is less than or equal to it. This is the definition we will use for AP Stats. There is another definition. If you want to know about that one, you can read about it in the textbook. In our definition, it is possible for an observation to fall at the 100th percentile. Here's an example. In a class of 25 students, suppose that 22 students are shorter than Brett. That is, Brett is the 23rd tallest. That means that Brett's percentile is computed as 23 divided by 25 is 0.92. We count the 23rd percent. Since he is the 23rd tallest, we do count him. So there's 23 out of 25 that are equal to his height or less. So he is at the 92 percentile. How do you interpret this? Well, this means that 92% of the students in the class are Brett's height or shorter. In stats, being able to interpret a statistic is very important. So pay attention to these interpretations. We will be asking you to interpret statistics on our exams. Another way to identify a location within a distribution is to use a cumulative relative frequency graph, sometimes called an ogive graph. That is the graph that appears in the bottom right-hand corner of this graph right here, of this slide right here. Now, over on the left, I have a frequency distribution table. Each category is 5 units wide. The second column shows the frequency for each bin or each category. You can see in the second category that there's 500 observations. It's at the very bottom. The relative frequency is the frequency divided by 500, and the cumulative relative frequency is a running total of the relative frequency. Okay, so relative, I'm going to walk you through how I calculate the cumulative relative frequency. In the first row, I have 0.4%, so I just carry that over to my cumulative relative frequency. In the second row, I have a relative frequency of 1.2, so I add that to my cumulative relative frequency to get a new cumulative relative frequency of 1.6, and so on. Now, let's look at this cumulative relative frequency graph and the histogram upon which it is based. In the range of about around 45 in my cumulative relative frequency, the ogive graph is at its steepest. Why is it steepest there? Well, that's where I have most of the data in the frequency histogram. So the steepest part of the ogive graph occurs where most of the data falls in my frequency histogram. You'll see also in the cumulative relative frequency graph that there's a flat spot. Why is there a flat spot from 70 to 80? Well, that's because there is no observations in the range 70 to 80. This is just a quick reminder about transformations, something we learned last chapter. What happens to the center, shape, and spread of a distribution if the original values are adjusted in a particular way? Here's my graph. Well, if I have my original graph and I add the value A to every single observation in the original graph, I'm just going to get a transformed graph that is shifted A units to the right. The center will increase by A units, the first quartile will increase by A units, the third quartile will increase by A units, but the spread does not change. The interquartile range is still the same, the standard deviation is still the same, also the shape does not change. All that is summarized right here on this slide. What happens if we multiply all the values in the original distribution by a value b? Well, that changes the spread this time. If b is less than 1, all the points will become a little bit closer to, will become a little bit smaller. I'm assuming all the values are greater than 0. So if b is less than 1, all the points will become smaller and the graph will become taller and more narrow. If b is greater than 1, then the graph will spread out more. All the values will increase by a factor of b, and the standard deviation will also increase by a factor of b. All that is summarized right here. You've seen this slide before. Now I want to talk about standardizing, because standardizing is just a variation of these transformations that we talked about. To standardize the value x in a distribution, we first subtract the mean of the distribution and then divide by the standard deviation sigma. So here's my formula for standardizing a value x. I subtract the mean and then divide by the standard deviation, and I get the standardized value, and we call that the z-score or the standardized score. And we can do this for every single distribution. Z-scores. What do z-scores tell us? Z-scores tell us how many standard deviations the original observation falls from the mean and in what direction. Observations greater than the mean have positive z-scores. Observations less than the mean have negative z-scores. Z-scores measure a location relative to the mean. Now let's talk about the normal distribution. The normal distributions come in many different shapes, but they're all defined by their mean and their standard deviation. When I say they're all defined by their mean and standard deviation, what do I mean? Well, if you know the mean and standard deviation, you know where every single point is on that graph. And this graph right here shows the proper notation for normal distributions. I write normal, and then I have two numbers in parentheses. The first number is always the mean. The second number is always the standard deviation. So my blue graph has a mean of 2 and a standard deviation of 2. It's tall and skinny. The red graph has is wider and has a standard deviation of 4. And the green graph is even wider yet, and it has a standard deviation of 6. And every location on that graph is again determined by that mathematical equation that you see. Normal distributions, here are some properties. They are symmetric, so we know that the mean is equal to the median. They are single-peaked. We sometimes refer to them as bell-shaped. And they have limits of plus or minus infinity. That means that these graphs right here, the low point goes all the way to negative infinity, and the high point, it's indefinite, it goes to positive infinity. The curve never touches the x-axis, no matter how close it gets. The total area under the curve is always equal to 1, regardless of the mean and standard deviation. So the normal distribution, the area under the curve is 1. Normal curves are completely described by their mean and their standard deviation. They're denoted n with the parentheses, then the mean, and then the standard deviation. The mean fixes the center of the curve. The standard deviation determines the spread. Distributions with smaller standard deviations are less spread out and more sharply peaked. Now, what happens if we standardize a normal distribution? If a variable x has a normal distribution with a mean mu and a standard deviation sigma, That means x is distributed normally with mean mu and standard deviation sigma. Then the standardized variable is that z-score right there. And we say that z follows a standard normal distribution. If I take every observation in a normal distribution and standardize it, I am left with the standard normal distribution. That is, z is distributed normally with a mean of 0 and a standard deviation of 1. Any normal distribution can be standardized. So here I have a normal distribution with a mean of 110 and a standard deviation of 20. I standardize that and I end up with a normal distribution that is the standard normal distribution. It has a mean of 0 and a standard deviation of 1. So the graph on the left, that is a normal distribution. That is like a vanilla milkshake. But the standard normal distribution on the right, that is the hot fudge sundae of normal distributions. That's an important one because we have a lot of information that we can use on the standard normal distribution. What are the properties of that standard normal distribution? Again, it is normal. It has a mean of 0. The standard deviation is 1. The total area under the standard normal curve, standard normal distribution is 1. So this all should be very familiar to you. But this last point is important. Specific areas under the curve can be found using a table or calculator. That's why we want to standardize normal distributions, because once they become standard normal distributions, we can use tables and calculators to figure out the specific areas found underneath the curve. I wanted to give you an example of a z-score calculation. Suppose the height of students in the classroom is normally distributed with a mean of 67 and a standard deviation of 4. Suppose Lynn's height is 65 inches. Her standardized score is this. I take my location at 65, I subtract the mean of 67, and then divide by the standard deviation, and I get a z-score of minus 0.5. What does that mean? Well, here's another interpretation. We want you to be sure you're able to interpret z-scores, because we can ask this on an exam. Interpretation. Lynn's height is 1/2 of a standard deviation below the mean of the class. That's the end of today's slides. Thank you very much.